Great, thanks. How are you? Let's wait maybe for another minute if anyone else shows up or shows up on the screen, and then we'll start. Okay, thank you for coming. And do you hear me at SDSU?
Yes.
Do you hear me? Is it loud enough?
Yeah, it's good enough.
Okay.
Thank you.
So what we are going to do today can be really squeezed in 5 minutes. Like 5 minutes and let you go. I will try to extend it a little so we do more baby steps. We carefully acquire initial basic concept, and I ask you to mobilize your forces for next week, which will be the hardest, two hardest lectures for the whole course. So there will be a piece of material that should be started and finished later. If you start now, it will be not good. So here is the plan, what we are going to do. So we are not yet starting computer labs. I will let you know when we will be doing them. So just spirit up, be ready to dive into that. I've seen that some of you were already contacting Doug Genuine and getting accounts on the computer cluster. So if you want to think ahead and maybe read something, the very introductory step or practical part will be to install on your computer, or it will be installed in the computer class, but you may want to read about these pieces of software and read what they are. So those are several examples of communication software that allow you to connect from regular desktop to a supercomputer. And some of you have already practiced it. So there are specific communication software. If you use Mac, then you just need terminal, and it has all other stuff inside there. If you are on the PC platform, they're here. And if you're using any Linux, you also shouldn't worry about it. Any Linux include these tools automatically. So I was trying to upload several documents, several handouts on the D2L, and I wonder, were you able to see them, or I should learn more how to do them? Okay, so there are 3 documents that I have uploaded a couple of hours ago. So some entertainment with biography of key contributors to add a little positive human factors to the boring class. Then there is a really simple, very short homework, which like 5 questions or 6 questions, and you answer with 6 sentences to your best of your knowledge. Do not worry, they are really simple, and if you sit here and talk or listen to what I'm talking, it shouldn't be a big deal. And as a question number 6 in this homework, I'm also asking you to start thinking ahead about your independent project that you will be doing at the very last month of the course. So some of you have already have an ideas. If you are in doubts, I offer you several options. So do not worry. It's just thinking ahead, so that there will be no surprise about the independent project. Okay, so we are done with administrative part. Or now I will provide a little bit more details when we go further.
Excuse me,
Scientific
Dr.
part, yes.
We do not have access to D2L from here, so can you send us an email maybe?
Absolutely.
Thank you.
If I'm forgetting to do it, please send me a prompt.
Sure.
I will reply.
Sure, I'll do that. Thank you.
Okay. So what we are going to do today scientifically, our goal is to quantify our vision, our modeling of materials, of molecules, and we are doing slow steps to accounting of properties of ions, electrons, and by now we just decided that we know position of those, momentum of those, and we are continuing this step, and at the end of maybe next Thursday, we will finally split electronic properties and ionic properties, and we will have 2 sets of equations, one set for electrons and another set for ions. But this separation is a significant contribution to human knowledge done in 30s before any computers were done, and it is a cornerstone of all computational chemistry. Therefore, we will go really tiny step, symbol by symbol, so that we have understanding on the initial step, and later we can accelerate on some less important things or on some technical. Okay, so here is the little document that you have in your D2L. So just faces of people and some of their biography. Actually, in the city of Los Alamos, main street, or one of the main streets, is named after this person because he was working there. Here I just show a screenshot of options for independent research project from last year, and you have some. You can see some handwritings because last year there were no electronic option. I was handing it out in paper form, and everyone was voting what to do or what not to do. So there are several lists and options. Okay, here's a little review of what we were doing 2 days ago. So we agreed that we know what a molecule is, and we agreed that a molecule has consists of ions, several ions and several electrons, and we need to take into account where they are. So here I'm just reproducing the image from last time where we specify position of ions, position of electrons, and we specify distances between them. And then we build a molecular Hamiltonian that contains 5 terms. 2 terms for kinetic energy, for motion of electrons and motion of ions, and 3 terms for potential energy. So the Coulomb propulsion of ions, Coulomb propulsion of electrons, and Coulomb attraction of electrons and ions. Right? Everything is simple. and they all depend on in form of operators or as on the position of ions and electrons. Yes, here it is. So 2 terms for kinetic and 3 terms for potential. And when we go from general verbal analysis to quantitative analysis, we are wishing to set up a molecular Hamiltonian, and we have a natural desire to solve it, right? So this molecular Hamiltonian consists of these 5 terms, and it does provide us with solution for eigen values and eigenvectors of this molecular Hamiltonian. And what is difficult, what is bad, is that those wave functions depend on too many variables. It's practically impossible to solve. So our plan is to try to separate variables, to go from one equation with many variables to fewer, to more equations with fewer variables. So it is an overview what we did during the last meeting. So we do need to apply some tricks. We want to separate the variables, but we see that there were, so to say, a bad guy, a term that depends both on electronic and ionic coordinates. And rigorously here the variables cannot be separated. So they cannot, but we really want it. And it is a typical situation in science when if something is not formally allowed but very desirable, one considers that some parts of the equations can be neglected because they are substantially smaller than other ones. And it is a very general approach to identify small part and neglect it. And as we go, we will do it. So right now, from our basic common sense, from our knowledge of science, we have an experience, a vision, an understanding that mass of an ion is typically much bigger than mass of an electron. So it is about factor 2000 or even more if they are heavy ions. And the velocities or momenta of electrons and ions are related to each other in comparable fractions. So electrons move at least 3 orders of magnitude quicker than ions. So momentum of an ion is approximately, well, much smaller than momentum of an electron. So if electrons are moving really quick, they're moving on a different time scales. Here, based on this vision, based on this assumption, based on this property, we can do a little intellectual step forward. We can assume that an electron or several electrons are automatically adjust their trajectory or their wave function shape to any motion of an ion, and they do it so quick so that ions think, well, ions do not think, but ions do not feel motion of electrons. So if someone change position of ions, electrons change their shapes instantaneously. This is not always right, but it is a good approximation. And if it is so, if the electrons are really much quicker, then from the point of view of an electron, please do not quote me on this phrase, because it is like very heretical point of view. So for electrons, ions can be considered as non-moving completely. So for some basic properties of electrons, one can neglect motion of ions and think that they are just positions, even not wave functions, just parameters. And this ideology, it is not very well verbalized, and it is typically skipped in the books, but it is a key step for further developments. So if we accept this assumption, then we are doing the next step. Among our 5 terms in the Hamiltonian, we associate our bad guy, our interaction between nuclei and electrons, to the electronic part. Because if ions are not moving, then this parameter, the position of an ion, is just a number. So this looks as not very rigorous and not very well verbalized, but this is an important part. Okay. If we agree on this, then the rest becomes more simple and technical. So here are 2 kinetic terms. Here are 2 electron-to-electron interactions. And here is our bad guy. So what we are doing, there is no mathematics. It is just accounting. We are reshuffling the order of the terms in the Hamiltonian and just think about them in a different way. So the kinetic energy of an ion and potential energy of ions interacting with ions can be fragmented as one part that affects only ions. And if we are staying on the point of view of electrons, this is not very important. And the rest of terms, they are directly related to electrons, or they are in a proximate way related to electrons. And so true electronic, and I do not know the right word, but it is like quasi-electronic, fake electronic term. But we are going to combine all these 3 together. And then we are splitting our molecular Hamiltonian onto completely ionic part and this pseudo-electronic part, which anyway depends on the position of ions, but here one adds an important verbal correction parametrically. So nothing changes in our notation, nothing changes in how we write things, but we say that it depends, this term depends on position of ions in a parametric form, which means if we do quantum mechanics, we do not consider positions of ions as operators. Here we consider position of ions as a numbers that are commuting with anything what we want, and they behave like a numbers. Ions are not operators, but numbers. Oh, not ions, positions. Positions of ions are not operators, but numbers. Okay. Let's do another little intellectual step. So we are doing really small step. I postpone explaining why it is necessary, but it is just a natural human curiosity. So what if we take this pseudo-electric Hamiltonian that depends on positions of ions as parameters. And depends on positions and momenta of electrons as operators. And then we try, or we ask someone to try for us to inspect what are eigenvalues and eigenenergies of this Schrodinger equation that we can build out of this fake electronic Hamiltonian. Later we will see that those solutions are helpful, but now we are just assume that what if we ask someone to solve it? What we expect to see? Well, there should be wave functions and eigenenergy. Wave functions will depend on positions of electrons in regular quantum way and on positions of ions in a parametric way. And eigenenergies also will depend on the same parameter, on the position of ions. So we will have completely manifold, complicated thing. Each Schrodinger equation is an eigenvalue problem. So it has infinite number of solutions. But those solutions are slightly varied if we assume that positions of ions are changed. So for each position of ions, there will be different set of solutions. Parameters. Positions of ions provide different solutions. Well, it is a helpful tool, but it doesn't solve the overall molecular Schrodinger equation. It is not a solution of the complete problem. It doesn't give us wave function of the whole molecule, but it is a useful tool to find wave function of the whole molecule. And here is a way how we can connect those two. So we can, done with curiosity, we can assume that those solutions, those wave functions, there are so many of those, and they are defined in any point of configuration space, that one can use them as a very good mathematical basis to represent any function. So if any function can be expanded in terms of those fake electronic wave functions, then we can compose our overall solution of molecular Hamiltonian as a superposition of those. Okay. So superposition. I will try to write an equation and then explain. So by setting up a summation of several of those basis functions with different coefficients, the result of such summation can end up in any function of our interest. So any function can be represented as a sum of basis functions with correct coefficient. Superposition, it is not not two words, it is one word. Its synonym, analogous word is sum, summation.
I have a question actually.
Yes, please.
I have a question. So you are saying that basically this Schrodinger equation that you are writing and the Hamiltonian depends upon the position of ions. Let's say that we have fixed the position of ions as you just said, but the position of electrons in electron cloud, they are changing all the time, right? So if we assume that, it means that eigenvalues are changing, basically eigenvectors are changing all the time. So my point is that, later on probably, I'm not going to jump too much ahead, but aren't these the eigenvalues, the energy separation of the orbitals or things like that, are they changing as well based on where electrons are?
So here we are assuming that positions of ions affect electronic properties.
Yes.
And we are closing our eyes when we want to see whether electrons affecting
Ions.
motion of ions.
Okay.
We will see that there is a little tiny term, and in most of our studies we are going to neglect it. The question is to correctly determine this term and proclaim that here it is, and we are going to neglect it. And it is what is done in 99.9 quantum chemical calculation. But I suggest that we approach this approximation very carefully, pronouncing each step as detailed as possible. And on our previous lecture, we agreed that for a time we forget about time. So we are not solving time-dependent Schrodinger equation. We are looking only on the eigenstates of time-independent, and dependence is left behind. So there is only static dependence on position. All any other words are just verbal argument. Formally,
So
we do not have time.
Okay, my point is that where this equation completely depends upon, based on this formulation, the position of electrons, right?
Position of ions.
Position
And
of electrons.
electrons are clouds, right? Wave functions.
Yes, clouds. Okay, yeah. So
probability distributions.
Okay. Ri, the small ri is not electron.
Small ri is position of an electron, but electron is never staying at specific position.
Exactly. But still the eigenvalues depend upon it, ri?
Eigenvalues depend on position of ions. Eigenvalues do not depend on position of electron.
Okay, that's good. Position of. Thank you.
Right, big function because it is a function of everything, of a whole molecule. And I'm just lazy, I'm skipping all this indices and parametric dependence. But we are going to represent any solution of this formal equation. It's not just any equation, it's molecular Schroedinger equation. So we are representing it as a summation or superposition. Please neglect, close the eyes on my last symbol. Okay. So it is very short notation, and I think for the rest of our discussion, for the rest of our lecture, we will not write any formulas more. We are just going to discuss what it is. So this symbol is a wave function, electronic wave function, which it is eigenfunction specified by index of state of eigenstate, and it depends directly. It depends on position of electrons as an argument, and depends on position of ions as an parameter. So by setting up a summation of many of such functions with the right coefficients, one can get anything. I'm not proclaiming that we have solved, but we will be going to we are going to find solution of our molecular Schrodinger equation in this functional form. Okay? And those coefficients should be taken with some specific coefficient. And these specific coefficients should depend on position of ions. Very good. We did a significant intellectual step. There is a lot of formal derivations that we will do next week, and I will try to make them as possible short and pleasant. But this point is very important. So we are looking for solution of molecular Hamiltonian in form of a summation of electronic wave functions with some coefficients that depend on position of ion. Here is verbalization of this situation. And those coefficients, as we can later see, they mathematically, they are just expansion coefficients, right? But scientifically, physically, they can be interpreted as wave function of ions, as probability amplitudes of an ion B in one or other place. We are really doing some very hard problem, or trying to analyze very hard problem. There are like hundreds of ions, thousands of electrons, and they all are not just positions, but we are looking distributions that depend on those things. And we are establishing a language to speak about this situation. So there is very simple, very natural and logical idea what we can do next. So we can take this functional form, plug it into molecular Schrodinger equation, and use it as an equation, as a tool to find those coefficients. And if we know by the set, if you know coefficients, then we know solution. And please do not worry. We are not going to solve anything. Though the problems are very complicated, and computers will solve them for us. But we just, as a big bosses, we want to give a right order to a computer and understand what will be done. So please be patient. It will be a little hard at the beginning, but the last 60% of the course will be simple and pleasant applications. It will be true chemical science. So plug it in. Yeah, it is just verbalization of what we do have. So we will take explicitly this expansion, plug it into molecular Hamiltonian, and try to find coefficients. What we have done by now, or what we plan to complete by the end of the next week, it will be not our ideal, in mathematical sense, separation of variables. What we are looking for is it is not our solution is not a product of two factors, that one factor depends on electrons, another on ions. It is a little bit more complicated. It is sum of products. But anyway, it is much easier than if one would try to solve the complete set of equations. So what we are going to do on the next two lectures, today we are going to finish much sooner than it is scheduled. But please think about it. Please analyze it at home, how you what you have heard. It is not much information, but it is very important step. The rest is built upon it. So let me announce in lay words what we are going to do in next week. So we are going to eliminate electronic wave functions by going from the explicit form of wave functions to matrix elements. Again, it is not any solutions. It is just abstract formulation of matrix elements of operators. And then on this way, at the same time, we will make a rigorous definition of potential energy surfaces, which are key concept in emission spectroscopy, in reaction dynamics. And we also will set up a very formal definition of non-adiabatic coupling that determines how the ions affect back the state of electrons. So we will provide a framework for both ions affecting electrons and electrons affecting ions. And after we set up a language, it will take about 2 lectures, the whole next week, we will go to practical steps how to solve it. Human society accumulated a lot of efficient and quick steps, and then we will, at the same time, we will go to practical steps applying those concepts to realistic models, starting with something really simple, working really quick, producing results in a few seconds, and ending up with research projects that will be unique. We will select such projects that no one else in the world did that, and many of them will be counted as true research. So if you want to invest your time in the subject on the weekend, I do have 2 options. So you can look on the chapter from the book that I have uploaded on D2L, or I can send it as an email. So it tells, it is as when you go to a doctor for something important, you sometimes go to another doctor for second opinion. I never did, but someone told me that one can do it. So if you do not believe me, you can look on what is written in the book and check whether it is truth or wrong. And another thing that we were doing in this class a year and a half ago, you can try to find in the internet or based on your own experience what is non-adiabatic coupling and build up a 1-page PowerPoint. So if you, with definition of non-adiabatic coupling, maybe some pictures. It is not required, but if you do, please send it to me. We will consider it as extra credit or use it in the course as a, you will help me to build to prepare next lecture. whatever you can say on this subject. I think everyone who will try will provide something unique and original. Even if you all try to do it, no one will say the same word. So I'm done for today with new material. If you have any questions, discussions, concerns, objections, suggestions, I'm very open, very happy to discuss.
Excuse me, Dr. Kilin. Can you explain me about those eigenvectors and eigenenergies? The eigenvectors in the previous slide.
Previous slide. So this equation.
Eigenvectors.
Oh, eigenvectors.
Yeah.
Okay. It is no. This is completely legitimate question, and let me open just a new empty page on a transparency and scratch some notes real quick. We want to keep this. Insert. Okay, so the question is, what are eigenvectors?
Yeah, what's the significance of those eigenvectors?
Eigenvectors. So this is a main concept of two branches of science or human knowledge of linear algebra and of quantum mechanics, and maybe, well, actually on many other branches, but here is most important. So if you want, I can provide something really, really simple, so that we do not go into complicated things. So all equations in quantum theory can be reduced to matrix form. So when we write that some operator acts on a function and provides eigenvalue and eigenvector, this notation, instead of function, one can convert operator into matrix, function into vector, and eigenvalue still remains a number. Simplest example of such sort of equations is in 2 dimensions, when we have matrix, operator is matrix I'm just lazy, and therefore I'm not providing specific numbers in position of those variables. But there are some numbers. Operator is represented as a matrix. Wave function is represented as set of elements. So there is this index I, but there is also an index 1. So this is a vector consisting of 2, or in most situations of much more basis elements. this is equal to this. So this equation in matrix form can be replicated, considered as two equations that are written in a usual way as a line. So this element times this element plus this and this will be equal to this number and this one. So you just do row by column multiplication and get two equations. When you try to solve them at the same time, it turns out that instead of one solution, which is typical situation for usual simple equation, you get at least two solutions. And if you have vectors of bigger dimension, you get more solutions. So as bigger the dimension of your vector, as more solution you have. So it is a difficulty that we have to accept, that there are some equations that have more than one solution. And solutions are represented or described in form of eigenvectors, which are specific numbers for those things. And each solution has a specific eigenvalue. So I'm not reproducing the whole course of linear algebra and quantum mechanics, but just pointing out what it is and where it comes from. Does it address what you were asking?
So in our problems, we are trying to find out these eigenvectors, or
well, we are not trying to find those ourselves. We are just accepting that in order to describe properties of materials, someone has to solve equations like this, and this someone will be our computer. But we want to give a very correct, very specific directions, very specific orders to computer, what to solve and what we want to get. Does it make sense?
Okay, makes sense.
Any other question? Okay, if not, I thank you for coming and looking forward to making our course interesting and pleasant. Thank you.
Great. Thank you very much. Have you heard about state space?
I've already studied these